Welcome to the Beals Science School. I've got a whole series of videos here that we're going to walk through significant figures. We're going to talk about why they're important. We're going to talk about how do you count them up. And we're going to get all the way to the point where we're doing operation rules with significant figures. Now, I have found through 20 years of teaching this that this is one of those things that really frustrates people because it's kind of abstract and it's kind of different and it's very new for a lot of us. But I'm going to help you out, and we're going to walk all the way through this step by step, and you're going to be successful with significant figures. They're also called significant digits, so you'll hear me say that a lot. Now, here's the thing. Why do we use them? So the question comes up all the time, how should I round my answer? Like, what should I round my answer to? But you can't answer that question and just say generically, well, round it to a few places or round it, because the correct answer in science and engineering is when you round it to the correct number of significant digits. So we'll get there, but like if I type this into my calculator is going to show that the answer to that problem is 12.132 square centimeters. Okay, question is, what should I round that to? Significant digits, the process that we're going to learn about over the course of these next few lectures, tells us that we need to round that answer to 12.1 square centimeters. Now, how do we know that? That's going to take a fair amount of learning. But first of all, what are significant figures and what are they useful for? In science, it's really important to be precise with our measurements. The numbers that we get from our measurements tell us how precise the measurement is. The more significant figures, in other words, the more numbers that we get from our measurements, as long as they're accurate numbers, that tells us that the measuring device and the person measuring was more precise. So in science, more precision means more significant figures, and in my class I say more significant figures is generally more better. Good thing I'm not an English teacher. Well, why do significant figures matter? I'd like to drive home 2 points. The first one being that they show the precision of the measurement, they show the precision of the measurer, and also tells us the accuracy of that, potentially. If we look at these two different measurements here, one of them has a lot more digits. It has a lot more figures. The one on this side with 1.09 grams goes down to the tenths, hundredths, and this one goes clear down several places. Now, assuming we used good equipment, this measurement is much more precise. This is a better measurement because, well, it has more digits, more significant digits. Significant figures are a standardized process that if everybody across the world uses this same process in science and engineering, we're always going to get to the same answers. Now imagine you're building a rocket booster to send satellites into space. Well, parts from that rocket booster are going to come from all over the world. They get assembled and then we shoot a rocket off into space. Now, everybody, everywhere that's working on this rocket booster needs to have a standardized system so that we all get to the same answers all the time. Significant figures helps with that. I've got another problem down here. If I put 34 divided by 10.1 into my calculator, I get this nice, big, long number. That was hard to say. And the problem with that is my calculator doesn't know what I should round that to. That's something that I have to round my answer to show the precision of the measurements. We're going to find out, but if you understand significant figures, everybody in the whole wide world, let me go back to that, would round that to 3.4, specifically 3.4 grams per milliliter. So how do significant figures show us the precision and therefore the accuracy of a measurement? I've got a graduated cylinder here, okay? That's my poor little drawing. Then I've got 3 graduated cylinders up there on the screen. Each one of them was a little more expensive than the one before it. I know that because I can see the precision of it. I can see the lines. Now this first one, if we're measuring volume, we can figure out why this idea of precision matters. And again, the idea of precision leads into the importance of significant figures. So if we fill these up, I've filled them up with water, and we're going to measure at the bottom of the meniscus. So let's come over here. If we look right here, we can see that is the volume of the water. Down here, we have 1 milliliter. Up here, we have 3 milliliters. Now, here's the thing. It is not at 3 milliliters. It is not at 1 milliliters, which means it is somewhere in between. And we can only logically say that it must be, I don't know, maybe about 2 milliliters. In other words, we have to estimate that measurement. We can't say 2.1, 2.3, 2.5 because there's nothing to give us that amount of precision. If we go to this next one over here, this is a little nicer graduated cylinder. We probably spend a little more money, and we can see it's got more measurements. Here's 2, here's 3. But we're somewhere in between the 2 and the 3, right? Actually, this line would represent 2.5 milliliters. So if we look, we're actually below 2.5, but we're above 2, or 2.0. So we could estimate this as something like, let's say 2.3 milliliters. Notice this last digit here was estimated. This last digit, our only digit, was estimated. Here's the 2, and we count up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines in between the 2 and the 3. So each line represents 0.1 milliliter. If we count it up, this is 2.1, 2.2, 2.3, 2.4. Ooh, it's right below the 2.4. So for certain, we are at 2.3 something, right? This is where we have to guess. That last number is estimated. So I said 2.38, but you might have said 2.39. Again, point being that last number is estimated. The other point being, look at the difference in all 3 of these, right? Let's go back. The difference in all 3 of these. This over here has more numbers. It has more digits in it. It has more significant figures. It's showing that we used more precise equipment than we did over here. Now, what about length? So length, if we look, this is 0. This is 1 centimeter. We've got 0.2, 0.4, 0.6, 0.8, and 1. And it falls somewhere right in here. We don't really know, but if this is 0.2, 0.4, 0.6, and this is 0.8, we either need to say that it's 0.6 or that it's 0.7. We can't guess any more precise than that. We should have got a better ruler. Indeed, we did down here, and I've just zoomed in. That's the same red line, but zoomed in because now we have this really nice precise ruler. Up here is 1 centimeter. It is broken up into, let's go back. It is broken up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. Each one of these then is 0.1 centimeter, which is 1 millimeter, but that's broken up even more. So this would be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. But we have more than that. Each one of these represents 0.02, 0.02. So if this is 0.6, this is 0.62, this is 0.64, look where we're at here. We can pretty effectively estimate that we're at 0.63 centimeters. Again, 0.63 centimeters is better than our best guess up here, which was 0.6. So the last number there is estimated. Now let's go to mass. These are 3 balances in my chemistry lab at my high school where I teach, and we use all 3 of them just kind of based on whatever our needs are at that moment. And oftentimes this is the one that I have out because, well, they're cheaper, still kind of expensive, cheaper than this one and cheaper than this one. So we don't feel quite so bad if something happens to this. Now, if we look, there is a big difference in the number of digits that they are capable of measuring. That's important because this one goes to the hundreds, thousandths, and 10,000ths. We're paying more and more and more as we're getting more precision and therefore more accuracy available in our measurements. So I dropped the same penny on each balance, right? And we can see over here we've got 2.48, 2.476, and then finally 2.77, 2.47, all these numbers. More numbers is more better when we're talking about our measurements. And that better measurement is going to give us more numbers. It's going to give us more accuracy when we use significant digits. So we know maybe now a little bit of why we need to understand significant digits and the importance of them, but how do we use them? This is one of the things that really starts to frustrate students. So check that next video, how to count significant digits. Thanks for watching. This is Craig Beals from Beals Science and the Beals Science School. Come on over to bealsscience.com and you're going to find all sorts of things, more lessons, more stuff to learn, and more crazy science stuff going on. Keep on learning.